All right. So, we should get started. So, we have to think about what are the bad cases and good cases for alpha beta pruning. So, this is in this slide I am showing you the bad case. Okay. I am a max, but I ordered my nodes as 2, 3, 4. If I ordered my nodes as 2, 3, 4, after I explore 2, I will have to explore 3 because 3 will finally be better. There is just no way I can not explore 3. I will have to explore 4 because 4 will be better. Similarly, for children of 2, the min node, I have ordered them 6, 4, 2. So, once I get the value 6, I will have to explore 4, I will have to explore 2 because 2 is the finally correct answer. So, if my better children or the best children are the rightmost or the last, I will have to explore everything, right. So, this is showing you an example where there will be no effect of alpha beta pruning. You can think about it, right. After you are done with this left subtree, my alpha would be 2, and once I go down and go to the first child of 3, my beta would be 7, not going to help, alpha is not greater than beta. Then beta would be 5, no point, alpha is not greater than beta. My beta would be 3, actually still no point, alpha is not greater than beta. So, I move up and my max becomes 3, and when my max becomes 3, alpha becomes 3. But again my beta will start from 8 and then go to 6 and then go to 4, alpha will never be able to be greater than beta, greater than equal to beta, and therefore, I will never be able to prune anything. How should I order these nodes so that I can prune something? It is very easy as a question if you have understood this far. So, for example, of the 3 subtrees 2, 3, 4, how should I order them so that I maximize the hope of pruning? 4, 3, 2, right, it is very simple. Once I got my best path early on, I have got the best bounds. If I have got the best bounds, my hope of pruning increases, right. Similarly, for the children of 4, how should I order them so that I can get the best pruning? 4, 6, 8, it is a min node. So, I start with the min first. So, I should do 4, 6, 8 first, and if I do this, then you will see that when I come to 3 and have explored 3, alpha will be 4, beta will be 3. Alpha will be greater than equal to beta, no point in exploring any further, we can prune and go back. So, in this way I will get the maximum pruning. Now, here is a question that I am going to answer in 2 slides, but I should have you start thinking. Suppose I give you the best pruning. Now, you know, remember that minimax search is b to the power m. Suppose in time complexity, suppose I give you the best ordering of nodes for the best pruning. What will be the time complexity? And how will you even compute it? Actually, let us answer that question first. This is the best pruning. What is happening? Now, to answer that question, let us first write a recurrence relation for just simple minimax search or depth first search. I have a branching factor b, let us say I have a root node at depth m. Let us say I define T of m be the time complexity of search for height m root node. So, it is a root node under which I have a tree of depth m. So, what will be the recurrence relation for T of m for regular minimax search in terms of let us say T of m minus 1? Somebody? T of m is the time complexity of searching, starting my search at a node which has a subtree of size m, depth m. Now, can I write Tm in terms of Tm minus 1? Tm is equal to b times Tm minus 1 plus some constant. What is the constant doing? It is just doing max or min, that sort of constant, or c, and it is not c, maybe plus b or whatever, you get the point. This T of m would be order b to the power m, big O of b to the power m. Okay. Now, comes the hard question, of course. Can we write a similar recurrence relation trying to represent T of m as lower order T of m minus 1, T of m minus 2, etc. for alpha beta pruning, if alpha beta pruning is being done on the tree with the best order of nodes. And this figure gives you the hint. For me to compute T of m, what do I absolutely have to compute? The correct value of the first child. I have to compute the correct value of the first child because only then I will get a good alpha, for example, assuming that my root is a max. This reverses if my root is a min, nothing changes. Now that I have computed the best value, I simply have to prove that it is the best value. Right? This is actually an insightful comment. Once I have evaluated the first child, and let's say the first child is optimal, I don't know it, but let's say the first child is optimal, then in other children I just need to prove that look, your child is not the best, I already have the best value. To prove that, for every child, every remaining child, I have to at least do one of their children. For the case of this subchild, for the case of this child, I have to do at least one expansion, the first child expansion, then I can prune the second and the third. Even for this 2, I have to first compute the first child, which gives me the 2, and then I can prune the second and the third. Now, with that intuition, can you tell me what is going to be the recurrence relation for T of m? What is the recurrence relation for T of m? Very good. What's your name? Kiran says, look, I have to do the next child, first child. That is going to be T of m minus 1 because that is holding a subtree of depth m minus 1. If my root is of depth m, my first child has subtree of depth m minus 1. But for the other children, how many other children do I have? B minus 1. For all the other children, I only have to evaluate one of their children, which would be at depth m minus 2. So, I get this as my recurrence relation. T of m is T m minus 1 plus b minus 1 times T of m minus 2. And that leads me to big O of b to the power m by 2. I get a half in the exponent, which is a substantial improvement actually, if you think about it. So now with that understanding, let us talk about alpha beta pruning. So, pruning does not affect the final result. Pruning prunes only the suboptimal nodes. Pruning prunes away the provably suboptimal nodes. It is not making any approximations per se. It always gets the optimal result if I can search till the very end, or even if not, whatever minimax does, it does the same thing, it gets the same result. Good move ordering makes a world of difference. And so now you should start thinking at the back of your mind, how can I order moves better? And we will come to that. But good move ordering improves the effectiveness of pruning significantly. Because in the worst case, no pruning will give me b to the m. In the best case, a lot of pruning can give me b to the m by 2. So, if I give you a minute and you were able to search till depth 4, because your complexity was b to the m, with good pruning, if you can get to b to the m by 2, that means you can effectively search till depth 8, and that is a big deal. In fact, we will later talk about how b to depth 4 in chess is an amateur, a novice, and how depth 8 is a good chess player, and how people like Gary Kasparov and Deep Blue would do depth till 12 and 14. So, just by searching for more depth, you will have a much better understanding of how to, you will know the better move basically, you can look ahead far enough. And now, I want to introduce one simple concept. This is the concept of meta reasoning. Meta reasoning means reasoning about reasoning. Whenever you hear the word meta, just expand it like this. Meta learning is learning about learning. That's it. Meta learning is actually a very famous field of research right now. It's one of the next big thing in machine learning. So, why is it called meta reasoning? Why is it reasoning about reasoning? So, what is it doing? What is alpha beta pruning doing? Alpha beta pruning is saying, so now think about or imagine that you are doing alpha beta pruning, you are the brain which is doing alpha beta pruning, then to you doing each search is like reasoning, is like thinking. How does a game player think? The game player thinks by going to all the children and figuring out their best values and etc., etc., etc. This is my thinking process in a game. And now why is the alpha beta pruning algorithm thinking about thinking? It is saying where should I expand, where should I not expand? Where should I go and try and figure out what is the best action, where should I say this is not interesting, let me not even go there. So, the process which figures out where to go and where not to go is a thinking process, the alpha beta pruning process, and that thinking process is deciding where to think, where to go expand, where not to go expand. So, this alpha beta pruning is sort of triaging all my subtrees and saying you the subtree looks promising to me, so I will go and explore you the subtree does not look promising to me, so I will not go and think about you. And so, therefore, it is sort of doing one kind of meta reasoning. I remember, I at this stage of my career, for example, have typically 10 students who are doing different research projects, right, or 20 students who are doing 10 research projects. And once in a while, I am driving in my car, I am taking a shower, and now the question I have to ask is, what do I think about? Project 1, project 2, project 3, project 4, project 10. And the process that makes me decide that, oh, project 1 is doing all right, let us not think about it. Project 2 is slightly stuck, how can we improve further, would be thinking about project 2, but the process that decides which project to think about is meta reasoning. And if you, in your assignments, for example, you may have to design a game, and you will have to do meta reasoning of a different nature. This also happens in practice. So, suppose there are two chess players, they are playing. Have you seen that as soon as they make a move, they hit the clock? Inside it is ingrained in their psyche. Even if you do not keep a clock there, you will make a move and bang something there. They have to bang it because their time is ticking. And as soon as they press the clock, the opponent's time starts clicking or ticking. So, what happens in these games is that each person is given a fixed amount of time. When you are thinking, your time is going, and when the other person is thinking, their time is going. And your goal is to think fastest based on the remaining time and make a move. Now, you may have met some people who just keep on thinking and thinking and thinking and do not really take an action. And that is also not ideal, because yes, of course, if you think more, you will probably take an optimal action, but optimal under what circumstances? If all your life you are only thinking to find the optimal action and never execute, you will never get the reward. You will never achieve what is the goal that you want to achieve. So, eventually in life, we have to think and then act, and we are given limited time to think, or we may decide to take more time to think, but then you have to pay the price, the cost of thinking further. And so, the meta reasoning process typically says, I have thought about it enough, I can't be sure that I am deciding an optimal action at this point, but if I trade off thinking more or just taking an action and moving forward, at this point I should say, let me take the action and not just continue thinking. And that process is also something like meta reasoning. It is saying that in this context, I should stop thinking and start acting. So, even there I am reasoning about how much to reason, right. And so, when you make your game bots, for example, on any game, you may be given a minute or 2 minutes or 5 minutes of playing time, your opponent may also be given the 5 minutes of playing time, and now you can say that I will plan the whole game and spend 4 minutes of the 5 minutes on the first move. Nobody can stop you from that, but that is not the ideal solution typically. Typically you take a small amount of time, you think a little bit and then you take an action. And now do you divide time per move equally, or do you spend more time earlier and less time later, or more time later and less time earlier, etc., etc. These are questions that you have to grapple with when you design your game bot, and all these questions come into the purview of meta reasoning. Okay. So, the next question is, how do I order my nodes such that I get best alpha beta pruning? Of course, I do not know the values, I can't go till the leaf every time. So, it is very hard, but what could I do? Can you guess? Can you give me a suggestion? I have many children, I need to figure out which child do I explore first, which child do I explore later, in the hope that it will give me the best alpha beta pruning. What can I do heuristically, let us say? Yes, what is your name? Jay.
You can have some probability that given my current state, what will be the maximum benefit I can get.
So, you can have an a priori evaluation function, some kind of a heuristic function, not probability of course, because probability, you can have a probability of winning as your possibility, or some evaluation function which says higher value is better, and figure out which node do you want to explore first, right. And this is what we are going to come to, right. But even there, this is an evaluation function without any search whatsoever. Suppose I wanted to use a little bit of search to figure out which is a better node to search. Well, remember, with every depth first search algorithm is also associated an iterative deepening depth first search algorithm. Now, with that hint, can you think of a good node ordering mechanism? Just building upon what Jay said, it is not that hard. What does iterative deepening do? It searches for one depth, then goes back, searches for second depth, then goes back, searches for third depth. Well, after it has done searching for first depth, it has some idea of which are better children. So, it can order them that way and search till second depth. After it has searched till second depth, hopefully it will do alpha beta pruning, so it will not be that bad, but then it will have more information, and so it can learn that information, use it to reorder all children and search it to third depth, and so on and so forth. So, this is one mechanism where people use iterative algorithms for better pruning. Yes, there is a question.
Sir, the functional value is only available at the leaf.
Very good. What is your name? Path. Give me 5 minutes, I am going to come to that. So, path makes a very important observation that the final value that we are updating, where are we updating it from? The leaves. So, if we do not search till the leaf, what do we know? We know nothing, right. So, we are going to, exactly that is what we are going to work on next. So, let us first see where we are in terms of chess, for example. So, earlier I showed you that even the universe cannot play chess, even if it plays chess from the very beginning of time, Big Bang. Well, that is no longer true, because with perfect alpha beta pruning, it can get to 10 to the 77, and that is less than the number of atoms we have. In fact, it is one order of magnitude less than the number of atoms universe has. So, technically universe can now play chess with this alpha beta pruning, but of course, is that good enough? No. There is no way that any computer is going to be able to make a chess algorithm which does this and searches till the leaf. We should stop. Thank you.